Okay, here's the second free response for the rotation test. First, let's scroll up so you can check just the parts you need to. And if you like, you can stick around for a detailed explanation of how to go about this one. And so we saw something like this on WebAssign. This is not the same problem, but I did use the image. And we have a round object, a marble, rolling down a ramp and then around a loop. And it's got some non-uniform density distribution that gives it a rotational inertia of 3/4 mr squared. And it's got a mass little m and a radius little r. And then this loop has a radius big R. And compared to big R, little r can be ignored. It can't be totally neglected, but it can be ignored when we're looking at it on the loop. And first thing is to draw a free body diagram. So you draw a large circle. Little tiny one is going to make it really hard to get all the points because I have to see the weight starting at the center and going straight down. I have to see the normal force starting at the point of contact and going right through the center. And I have to see static friction starting at the contact point and being perpendicular to the normal force parallel to the ramp. And so +2 if you didn't make any mistakes, +1 if for one mistake. And one mistake more than a few people made is they drew what it would be like if the ramp was tilted this way. And that's a mistake. It's not tilted this way. And so this is the free body diagram. The normal force has to go up and to your right. Next, we want to show the angular acceleration is given by this equation. And that's tough to do, but not as tough as it looks here, because I'm doing two different ways. And so the first way, I'm going to sum the torques about the contact point. And so the weight is the only thing that has a torque, because the normal force and friction have no lever arms about the contact point. But the weight isn't perpendicular to the contact point. And so we have to figure out what the perpendicular component is. This is theta, and so it's opposite theta, so it's mg sine theta. Plus, what if theta is 0? Then there's no torque. Sine of 0 is 0, so if you have a cosine there, that wouldn't work. And then don't forget the lever arm, which would be the radius of the marble. And then the rotational inertia, I need to use parallel axis theorem for, because I'm summing the torques about the contact point. So it's the rotational inertia about the center plus mh squared, where h is the radius of the marble. H is always the distance from the center to the rotation axis, which I made the contact point. And so if you do it this way, this is hard to set up, but once you do, it's just one equation, solve for alpha, and you get what was asked for. How about the other way to do it? You're going to sum the torques about the center. And so now the only thing with torque is friction. And so the weight doesn't have a torque because it has no lever arm, and the normal force doesn't have a torque. It has a lever arm, but it's parallel to the lever arm, so no torque from it. And so it's just the force of static friction times the radius is the torque equals I alpha. And so force of friction is I alpha over R, and I is just the 3/4 mr squared that was given. And so that's one equation. And then I don't know what friction is. You can't say friction equals mu times the normal force because it's less than or equal to. It's only as big as it needs to be. We don't know where it's at, if it's at its maximum or anything. And so to get the other equation for friction, I sum the forces and set it equal to ma. So I have a coordinate system like this, and plus x is going down. And so mg sine theta is the positive x force. Friction is a negative x force. That equals ma. A is alpha r. So I substitute for that. And I have an equation for friction here. So I put that into there and simplify it, and I get what they asked for. I think there's one more step for you to take here, but I didn't go all the way. It gives you this. And so try both ways. If you did it this way, try this way. If you did it this way, try it the other way. Learn how to do this. One of the hardest skills we learned during the year. And now we want to figure out how fast the marble will be going at the bottom of the track. And so energy is the way to go. We wouldn't want to use alpha because the track doesn't stay straight the whole time here. You could get pretty close to it, but I don't think anybody did it that way. You would have got some credit if you did it successfully. So the initial energy equals the final, I think, is the way to go. I start out with gravitational potential, and I end up with two kinds of kinetic energy. So you could say plus KT plus KR. And so this is K translational, K rotational, and the height is 3R. That's from up here. And I'm solving for how fast it goes. And then I put in I as 3/4 mr squared. You don't have to use the parallel axis theorem because we're breaking rotation up into two parts, translational and rotational about the center. And then V is omega r, so omega is V over r, and it's little r. Kind of hard to see here. And so you get V squared over r squared, and so the r squareds go, the m's go, and prettied up here, you have to get a common denominator here, and you end up with 7/8 V squared is 3gr, and so V is square root of 24/7 gr. A lot of people got that right, and this is a tough problem. And just if you made a mistake along the way and got 2 points, it's still doing really well. And so let's look at the last parts. And so we have the object is going to reach point A, which was on the side of the track. So the normal force is pushing toward the center, and weight is down. It's kind of hard to see what static friction would be. There is static friction, and it would be up. That's not easy to come up with, but it doesn't really enter this problem. And so I want to know the force of the track on the object. It is the normal force. Technically, somebody might say, hey, wait a minute. The friction also is a force of the track on the object. Really should say normal force here. That didn't trip anybody up, but if you did do some sort of magnitude with friction or something, I would have given you full credit on this. So it's really just I want the normal force. And so some of the forces in the x equals ma, and the only force in the x is the normal force, and the acceleration is v squared over r, and that's big R now, the radius of the loop. And so I need to figure out how fast it's going. And so it's really another problem like this, but a little tougher, depending on how you do it. I said that zero height was the bottom of the track. And so I have gravitational potential, kinetic, rotational kinetic, and still gravitational potential. Another option would be to say the height is only 2r and not have this term. You can see it works out to be the same thing. You can see I took a few shortcuts here because I did it up here. And that's okay on a test. Hey, I just did this. I can start where I left off up here. And so when you get down to this step, you end up with some different numbers. And so you end up with the square root of 16/7 gr. Put that in for v, square it, and you get 16/7 mg. And then finally, if the entire track were frictionless, how would it affect the answer to C? And so C is asking for the speed. And so you have to say, is it going to be faster or slower or the same? Some people were answering some other question like the time or something. And so focus in on what it's about. More speed, less speed, same speed. And then any reasonable explanation. Most people got this, so I just made that worth 1 point. Typically you get 1 point for that and then 1 point for the explanation, but I just gave 1 point for the whole thing. And so let's move on to the simple harmonic motion